What's up, everyone? How's it going? In today's lecture, we will be discussing hemodynamics, or the dynamics of blood flow. So today we're going to be talking a lot about blood velocity, pressures, blood flow, resistances, and so we sort of brushed up on these topics within that overview to the circulation video, but today we'll go a little bit more in detail with those terms and with some equations that relate those terms. First, let's distinguish between the term blood velocity and blood flow. Velocity in this sense is going to refer to linear velocity, which is a distance over a unit of time. For example, that could be meters per second, centimeters per second. And so when we look at blood velocity, we're looking at how far is this blood traveling over what unit of time. Blood flow, or volume flow, is going to refer to the blood volume per unit of time. Typically in the cardiovascular system, we measure flow in liters per minute. Now, these two terms are related by the equation velocity equals blood flow over cross-sectional area. So velocity is not only going to be determined by how much blood is moving, but also the size of the container, or in our case, the vessel that it is moving through. So for example, let's say that flow is constant. The starting flow, the differences in pressure between the start and the final is going to be 10 milliliters per second. So at this given vessel, let's say, it's starting with a cross-sectional area of 2 centimeters squared. So the velocity here is going to be 5 centimeters per second. Now, if we it looks like fivefold. If we increase that cross-sectional area fivefold, then we could see that is going to lower the blood velocity. That blood is going to be distributed over a greater cross-sectional area, and that's going to slow down the amount of distance that it's going to move. So by multiplying the cross-sectional area fivefold, the velocity is decreased fivefold. And then by, again, reducing that cross-sectional area down to 1 centimeter, we see that velocity significantly increases. So by decreasing the area tenfold, the velocity increases tenfold. So again, just relating these together, velocity is going to be the distance per unit of time, which is dictated by the volume of blood flow moving per unit of time, and also the cross-sectional area of the vessels that it's moving through. We've already discussed blood pressure throughout the systemic circulation. Pressure is going to be highest in the aorta and the arterioles, and is going to decrease as we go from the arterioles to the capillaries to the venules to the veins. So blood pressure decreases throughout the systemic circulation. When we look at blood velocity, we see that again, blood velocity is going to be highest in the aorta because blood flow is going to be high, but also the cross-sectional area is the lowest. It is just one vessel that stems out from the left ventricle, so that total cross-sectional area is very low compared to the rest of the vessels. And so as we go from the aorta to the arteries to the arterioles, we get more and more cross-sectional area of those vessels. And we hit a peak in the capillaries where we have the greatest amount of cross-sectional area. So therefore, the blood velocity at the capillaries is actually the lowest. And again, this is not necessarily a bad thing, because at the capillaries, this is where we get the exchange of O2 and CO2 and nutrients. And so by having a low velocity in this area, we are able to optimize the exchange of those materials. And then again, cross-sectional area starts to decrease as we go into the venules and the veins, and we see that because of that, blood velocity does increase. So again, just relating all of these things together, velocity is determined not only by the amount of blood, that blood flow, but also by cross-sectional area. And so velocity is going to be highest in the aorta and then lowest in the capillaries. In order to understand how blood flows throughout the body, we first have to talk about the determinants of blood flow, or the different factors that impact blood flow. Now, blood is a complex fluid. Not only is it made up of water, but it's made up of different proteins and different cells. And so when we describe these equations today and all these different dynamics of fluid movement, we're really going to assume we're talking about a Newtonian fluid, which is, textbook definition is a fluid whose shear stress increases along proportionally with shear strain. And so again, we won't be getting into those things necessarily today, but we're sort of more so talking about the movement of water. And now blood is going to behave in this similar manner, but we are making some assumptions here today. And so, for example, we're talking about steady flow and non-pulsatile flow. When we know that, in the arterial side of the circulation, that flow is going to be a little bit more pulsatile due to the phases of the heart. Again, today we're really going to focus on this steady flow of fluid. And we're going to mainly, assume that we're talking about laminar flow, which is when the fluid moves as individual parallel layers at different velocities. And that's depicted here in this figure to the right, where you have these individual vectors of the fluid that is moving forward, and they are all parallel to one another, right? Moving in that sort of same direction. However, the blood flow does not always behave in this manner, and then especially when you get a change in cross-sectional area to the blood vessels, like if you are going from a smaller vessel to a bigger vessel or vice versa, when there's that change in cross-sectional area, a lot of times this blood flow can get turbulent. And that means that, some of these individual vectors do not remain in that parallel direction, and the blood flow becomes a little bit more chaotic. And this can, create different stresses and pressures against the walls of the vessel that can ultimately impact blood flow. But again, I don't want to get too complicated or too bogged down into a lot of these things. Today, we're mostly talking about the different things that are going to impact pressure, that impact resistance, and then therefore impact blood flow. The first determinant of blood flow that we'll discuss today is hydrostatic pressure. And the definition for hydrostatic pressure is the pressure of a fluid associated with the height of the fluid of a column above a reference point. And today, since we're talking about the cardiovascular system, our reference point is going to be the heart, the density of the fluid, and acceleration due to gravity. Here you can see that terminology displayed in an equation where hydrostatic pressure, again, is equal to the height of the column, the density of the fluid, and the constant of gravity. So now, here on Earth, your gravity is going to be a constant. Remember that. It's going to be 9.8 meters per second squared. That's the same no matter where you are within Earth's atmosphere. Now, viscosity or density of the fluid can change, but for the most part, second to second, minute to minute, this isn't going to differentiate too much. So a lot of times you could simplify this equation to hydrostatic pressure is going to be equal to the height of the column. And that indicates that the longer the tube or the greater the height, the higher the pressure. So let's talk about that in this figure here. When you are lying down, your blood is going to be sort of equally distributed if you looked at your torso, your head, your feet, because, as far as the height of the column is concerned, you're basically within that same plane. However, when you stand up, what happens? Well, gravity is going to pull that blood towards your lower limbs. So when we're discussing hydrostatic pressure, we can see that the pressure that is going to be at the feet is going to be a lot greater than it is at a little bit higher up on the legs, and then at the torso, because if we're looking from reference of the heart, the height of that column is much greater from the heart to the feet than it is to, let's say, the torso. So a greater hydrostatic pressure is going to be experienced at the feet when standing upright than closer to the heart will be. We will actually talk about in the future of why this can be a problem when it comes to keeping up with cardiac output and stroke volume. But you could see sort of right away that when we're standing, most of this blood volume is going to drop down below. And if we want to keep up with stroke volume and cardiac output, we need to find a way to keep this venous return up so it returns back to the heart and we can maintain those stroke volumes. This is a problem associated with upright organisms. If you looked at a dog, for example, their heart is going to be more in line with their circulation, so not as much hydrostatic pressure at the feet of this or at the paws of this animal as compared to humans. Let's put a pin on that concept for a later date and now just discuss again how hydrostatic pressure or the height of a column is ultimately going to impact blood flow. In figure A, you can see that we have two different columns, which are going to be designated as uppercase R1 and uppercase R2. In R1, we're going to have fluid to this certain height, known as H1. And so the amount of fluid that flows from the column on the left to the column on the right is going to be due to the height of that column and therefore the initial pressure of that fluid minus the ending pressure. And since R2 doesn't have any liquid in it, there's no resistance or no real pressure that is opposing this fluid that is traveling from R1. And so we are starting with a flow of 5 milliliters per second, let's say. So now let's manipulate some of those variables. If we increase now the height of the fluid of R1, well, we know from the hydrostatic pressure equation that that's going to mean a greater initial starting pressure. And by doubling the height of fluid within this column, the flow is going to increase proportionally. So we doubled the height of fluid in this column, and therefore we doubled the flow of fluid from R1 to R2. Now, in figure C here, we see that we have doubled the height of the first column, except now we have also put fluid in this second column that is equal to about 1/2 the height of R1. So the flow is going to look very similar to how it did in figure A here, because even though that overall fluid has increased, when you look at the differences between these two, it is going to be the same. Then in D, we're saying that the column of R1 and the column of R2 have the same heights of fluid. So therefore, since these heights are the same, the pressures are going to be the same, and therefore there is no flow moving from column to column. So to simplify hydrostatic pressure, flow is proportional to the starting pressure minus the ending pressure. And that starting pressure minus ending pressure is equal to delta P. Well, as we just discussed, that delta P is going to be determined by the height of each columnar fluid. So if we simplify that equation, that means that flow, which is equal to delta P, also means that flow is proportional to the height of the column of fluid. So hydrostatic pressure means that the height or our posture is ultimately going to determine blood flow. But also the length of our blood vessels, the radius of our blood vessels, and the viscosity of our blood are also going to determine blood flow. So let's use a similar model to see the effects of blood vessel length, blood vessel radius, and blood viscosity. And so in these 4 examples, we're going to see that we have a column of fluid at the same starting height, so hydrostatic pressure won't be discussed because those heights are all going to be the same. But we are going to have the length of a blood vessel, we're going to have the radius of that blood vessel, and then we're going to have the viscosity of that fluid or that blood in our case. So if we take this starting reference and we doubled the length of our blood vessel or our tube in this case, the flow is going to decrease by 50%. There is a greater amount of length that fluid has to travel, and the flow that ultimately is going to come out of that tube with a given starting pressure is going to decrease by half when we double that length. If we increase the viscosity of the blood or the thickness of the blood flow is also going to decrease. And so we see in the example D down below that we are going to double the viscosity or thickness of the blood, and that's going to result in a 50% reduction. So both blood vessel length and blood viscosity are inversely proportional, meaning that if we double the blood vessel length or double viscosity, well then in both cases the blood flow is going to decrease by 50%. However, radius of blood vessels, as we discussed, is really going to have a dramatic impact on our blood flow. By, in this case, doubling the size of the radius, what happens is that blood flow increases 16-fold. And that is why, as we'll see throughout these lectures, that really when the body needs to make changes in blood flow, what's going to happen is that we are going to change the size of blood vessel radius in order to really regulate blood flow throughout the body. When you put all of those variables together, you get what is called Poiseuille's law, which determines that blood flow is proportional to pi times delta P, or initial starting pressure minus ending pressure, times radius to the fourth power, over 8 times viscosity times blood vessel length. And so since pi and 8 are constants, you really don't need to worry about it as far as physiology is concerned. But the pressures throughout the body are going to ultimately determine blood flow, as we know. But again, the radius of those blood vessels, that's going to be the most important factor when it comes to blood flow throughout the circulation. And so if we want to increase blood flow to a certain area, the most beneficial way of doing that is by increasing the radius of those blood vessels, because again, you are going to get, for every time you double the radius of that blood vessel, you get a 16-fold increase within that blood flow. But also the opposite effect also holds true. So if you want to decrease blood flow to a certain area, you would then want to decrease blood vessel radius. And we do this by vasoconstriction of those vessels. Again, the other two factors, viscosity and blood vessel length, if you increase viscosity or you increase blood vessel length, you will decrease blood flow, and so again, those are inversely proportional. If you doubled either one of these factors, you would decrease blood flow by 50%. Resistance is going to be the opposition to blood flow. So if we wanted to quantify it, it is going to be the ratio of pressure change, or delta P, over flow. And so this is just a rearranging of the hydraulic resistance equation, which is pressure is equal to flow times resistance. And remember, overall for our bodies, we use mean arterial pressure is equal to cardiac output times total peripheral resistance. Now, what determines resistance? Well, we just discussed it on the last two slides. The blood vessel radius, the viscosity of the blood, and blood vessel length are ultimately going to determine the resistance to blood flow. And so the primary determinant of resistance is blood vessel radius, as we discussed. And remember, the reason why it's the primary determinant, because that those changes are to the fourth power. And so if you have a change in the blood vessel radius, you are going to have a significant change to both resistance and then therefore blood flow. And so, throughout our body, when there needs to be a change in either blood flow, resistance, and then therefore pressure, this is how the body will adjust those things within our circulation. So by adjusting the radius of our vessels, we have significant changes to resistance, flow, and therefore pressure. And so if you constrict the vessels, right? If you vasoconstrict, what occurs is that blood vessel radius decreases, and thus resistance would increase. If you increase resistance, you increase pressure, but you decrease flow. So now, where we're going to see the highest resistance throughout the circulation is going to be within the arterioles. And so that's why they're known as the resistance vessels. So when there needs to be changes to resistance, pressure, or flow, and we need to use the circulation or the blood vessels in order to do that, this is ultimately what we are going to do. We are going to determine the contraction of those smooth muscles that surround the arterioles, and if we need to increase resistance and pressure, we are going to vasoconstrict, decrease the radius. If we need to lower resistance and therefore lower pressure, well then those smooth muscles are going to relax and we're going to vasodilate. To summarize the effects of blood vessel radius on our cardiovascular system and hemodynamics, let's just again run through how the radius impacts resistance, flow, and pressure. When we vasodilate a blood vessel, what happens is that the resistance of that vessel will decrease due to the increasing of that radius. That in turn will lower pressures and increase flow through that vessel. And so when there needs to be an increase in blood flow to a certain area of the body, or there needs to be a drop in resistance and pressure, then vessels will dilate by smooth muscle relaxing. However, when there needs to be blood flow cut off to a certain area of the body, the vessels will vasoconstrict. Those smooth muscles will contract, the vessel radius decreases, and what that does is decrease blood flow to that area of the body, but overall, that increases total peripheral resistance, and vasoconstriction also then will increase mean arterial pressure. As we discussed in our circulation overview lecture, the blood vessels of the entire circulation are mostly set up in a parallel resistance, meaning that all of the blood pathways to these different organs of the body run parallel to one another. However, in the renal circulation and the splanchnic circulation, what we are going to see is that those vascular beds actually run in a series. Let's talk about some differences between a series and parallel setup and what effects that has on overall resistance and regulation of blood flow. So in a series setup, there's only one pathway for fluid to travel down. So if there's a red blood cell and there are all these different organs along the way, well, that blood cell has to travel to the first destination before going to the second destination and then the third. But in a parallel setup, that one blood vessel is going to have a determined route that it is going to travel down, and it doesn't need to travel to the other organs before heading to its destination. And so in a series setup, at steady state, flow at a given segment must be the same at all other segments. So what you're going to see is blood flow is basically going to be determined by, again, the starting pressure and the ending pressure. However, there is differences in pressure gradients due to the individual resistances. And so what you are going to see overall is that the resistance, the total resistance in a series, is equal to the sum of the individual resistances. So even if just one of these areas increases resistance, well, that's going to increase the total resistance within this vasculature setup. When blood vessels are set up parallel to one another at steady state, the total blood flow through the entire setup is going to be equal to the sum of the individual blood flow through each segment. And so this is advantageous in a sense because a parallel setup is going to have a better control of blood flow because there are multiple pathways for that fluid to travel. So we've discussed earlier about exercise, and this is a scenario where we need to increase blood flow to the skeletal muscles. And so if we want to, in a parallel setup, we could then increase the blood flow here to, let's say, section 1, and then take away blood flow from other areas of the body. And so we're able to better regulate how blood flow is distributed in a parallel resistance. In a parallel setup, we're going to see that the pressure gradients are going to be the same as opposed to a series, which each individual resistance has its own pressure gradient. And then also in the parallel setup, we have a term called conductance flow, which is going to be the reciprocal of resistance. And so the reciprocal of resistance, that conductance, is equal to the conductance of each individual segment. And so what we see overall is that resistance is higher in a series setup than compared to a parallel setup. So let's use some math to show how a parallel system has less resistance than a series system. And so remember the equations from the last couple of slides. A series system has a total resistance of the individual resistances, and in a parallel system, 1 over total resistance is equal to the reciprocal of each individual resistance. And so let's see how this plays out when we put all the resistances equal to 2. So just ignore the units. Let's just say that looking at parallel and series, that all of these are just equal to 2. So they are the exact same. The total resistance for a series system using that would then be equal to 6. While if we did the math for a parallel system, then that would equal, each individual reciprocal would equal up to 3 over 2. And again, since this is 1 over, we would just flip this to see that our total resistance would be equal to 2 over 3. Much less than the series system. So again, overall total resistance in a parallel system is significantly lower than that for a system in series. It's important to note that using that math that you could see that the resistance, the total resistance for a parallel system is actually less than the individual resistances. Remember, these are reciprocals, so if our resistance was 2 for each, our total resistance in the parallel setup actually wound up being less. And this is different than the series, which again, the total resistance is equal to the sum of the individual resistances. An advantage of the parallel system to a system in a series is that we can better distribute blood flow. There's more pathways for that blood to be distributed across. So if we need to take blood from one area of the body and redistribute it to an area of the blood that needs it more for a given situation, such as exercise, well then the parallel system allows us to redistribute that blood flow. So to review, a parallel setup has a lower total resistance than a series setup, and a parallel setup is better able to regulate the distribution of blood flow. And so there are more pathways in a parallel setup. So, we can redirect blood from one area of the body to another area of the body. And again, we use the example of exercise to sort of show this. So if you said that this R1 here was the resistance or, blood flow heading to the stomach, this pathway here in the middle is going to head to the skeletal muscle, and this third one down below is heading to the brain. Well, if we started to exercise, then the demand for blood flow would increase here in Q2. And so in order to get more blood flow for a given total amount of blood flow, well, if we wanted to then redistribute to here, we could take the blood flow from the stomach, or a lot of the blood flow from the stomach, and then redistribute it to those skeletal muscles. Now, how does that look physiologically? Well, we discussed earlier about vasoconstriction and vasodilation. So to the stomach, we can reduce blood flow by vasoconstricting, which is going to increase resistance here and decrease blood flow heading to the stomach. And then to the skeletal muscles, we can vasodilate, which lowers resistance headed to the skeletal muscle and increases blood flow to the skeletal muscle. So this is what occurs during exercise. We have vasoconstriction of the splanchnic organs, like the gastrointestinal organs, because they don't need as high oxygen demand during this exercise period. And we redistribute that blood to the skeletal muscles by vasodilating those blood pathways, and therefore the skeletal muscle can receive more blood flow. So today we talked all about hemodynamics. We talked about blood velocity, blood flow, pressures. We talked about resistances. We talked about how that changes the determinants of blood flow. And so there are a lot of things here to review. This was a very content-heavy lecture. So I definitely recommend going back, reviewing over these terms, reviewing over these equations, and what that means overall for cardiovascular physiology. Being able to tie in resistance and how that relates to pressure and how that relates to blood flow. We also talked about how blood vessel radius can change in order to impact resistance, pressure, and flow. And that's going to be one of the most talked about aspects of this class because, as we're going to see, based on the metabolic demand and based on what's going on in the body, we are going to vasoconstrict and vasodilate our vessels in order to change those resistances, in order to change pressure, in order to change blood flow. Thank you guys so much for watching this lecture. I'll see you in the next video.